Okay, part two of the standing waves lecture is concerned with the trigonometry. The trigonometry will explain how the little pattern expressions that you saw in the previous lecture essentially get picked up. Okay, so let's go ahead and start by defining things. Okay, so first of all, we have the x-axis like so, and the spring is stretched out along the x-axis, and then the displacement from the equilibrium position perpendicular to that, that's the direction y. Okay, and then right here, for example, is the spring before we form the interference pattern. Okay, right here is one person, we'll say, that's holding onto the spring at the origin. And then over here is the other person. Let's say that person is a distance L away. Okay, the interference pattern is formed by the superposition of two waves. The simple periodic waves that I send down in this direction, and then the simple periodic waves that reflect back to me. So basically what we have to do here is we have to add together two functions. So those functions are added together in the following way. Okay, the overall wave form that we see is equal to, first of all, the waves that I transmit down the length of spring, plus then the waves that reflect back to me. These two functions will then combine together, superimpose, as we say, to produce the standing wave interference pattern. Okay, now what are these functions? Well, first of all, let's say that I transmit waves down the length of spring, and they're just simple periodic waves. The waves that then therefore reflect back to me are identical to those waves in every way, except for one thing. They're going to be reflecting at a closed end. This then means that the reflections are pi radians out of phase with respect to the waves that I initially transmit. So here are the two functions then. Okay, so first of all, the transmissions. The transmissions I'm going to simply write in the following way. So what I have here are simple periodic waves that are propagating to the right-hand side on the spring. And then the reflections are identical to these guys here in every way. That is, same amplitude, same wave number, same angular frequency, except they are pi radians out of phase, and they're propagating to the left. So then therefore the reflections look like this. Like so. So notice the difference here with respect to the reflections as opposed to the original transmissions. First of all, there's a plus sign here like so. This indicates that the reflections are propagating to the left. And then I have right here a phase angle of pi. As I said, because we're reflecting at a closed end, the reflections are pi radians out of phase with respect to the original transmissions. As we'll see when I run through the trig here in just a moment, it doesn't matter if we think of this right here as a plus or a minus. Okay, now how does this then add together to ultimately produce the standing wave pattern that we saw? Well, it involves two trigonometric identities. The first trig identity is just going to be applied to the reflections themselves. So let's just take a look at these guys right here. Okay, so the reflections then, let me just rewrite the expression here. However, I'm now going to write it in the following way. Like so. And now think of this as the following. Cosine of one angle plus or minus another. So I'm going to use either the addition or the subtraction identity for cosine. It doesn't matter which, however. So here's then how I apply that trig identity. Okay, first of all, amplitude A. Okay, and then we have cosine of the first angle times cosine of the second angle. And then if you recall, there is a sign switch. So then therefore, if it's a plus, it's now a minus. And then if it was a minus, it's now a plus. And then we have sine of the first angle times sine of the second. And we end up with this messy expression here, but it does begin to simplify for us rather nicely. Okay, first of all, in the second term, notice that I have right here the sine of pi. Sine of 180 degrees is equal to 0. So then therefore all of this stuff here just drops out. This ultimately explains why, that it really doesn't matter if you write this as a plus or a minus because all of this stuff drops out anyway. And then over here on the left-hand side, we have right here cosine of pi. Cosine of pi, remember, is equal to -1. So then therefore, if I take this negative sign and I pull it out in front, the reflections then therefore simplify to become the following. Like so. And now I'm going to go back up to the top board and replace the reflections term with this guy right here. So essentially, when I apply this first trig identity, it just gets rid of this pi term and tacks on a negative sign here to reflections. Okay, let me just go ahead and erase the board and rewrite. Okay, so now here's what I have. First of all, I have the transmissions, which I haven't touched yet. These guys here, and now the reflections. So these guys here. And now I apply another trigonometric identity. This trigonometric identity, however, is one of the lesser known ones. Okay, so that trigonometric identity, one of the lesser known ones, is as follows. And because I have trouble remembering it sometimes, I have to check my notes here. Okay, so this second trig identity, let me write it down for you, is the following. Cosine of A minus cosine of B. In other words, cosine of one angle minus the cosine of another angle. Have you guys ever seen this trig identity before? It's a double sine function. It's specifically the following. Like so. Have you ever seen this trig identity before? It is one of the lesser known ones. Okay. Regardless, however, if you were to prove it, you would have to use, for example, the positive, or you would have to use the addition identity for sine along with a half angle identity, the subtraction identity for sine along with a half angle identity, and then a bunch of stuff happens, and then blah, blah, blah. You ultimately end up with this. Okay, regardless, however, of course, we don't have to prove this trig identity. We're just going to use it here. Now, it looks initially like a mess, but it simplifies this expression here very nicely. All right, so now when I apply that trig identity, first of all, first and foremost, notice that we have here this 2, and then multiplied by the amplitude A, like so. So if you look at my standing waves demonstration video, you'll notice immediately that the amplitude of the standing wave is large. And the reason for that is because of this guy here that we pick up through this trig identity. Okay, now I've got this first sine term here. So sine of A plus B. So sine of A, and then plus B, and then all divided by 2. Okay, this will simplify for us very nicely in just a few moments. Okay, and then I have the second sine term. So sine of B, like so, and then minus A, like so, all divided by 2. Like this. Okay, now let's go ahead and simplify. So in this term right here, notice that the negative omega t and the positive omega t cancels out. And then you have your kx plus kx for 2kx, but then divided by 2. So we just end up here with sine kx. Okay, and then over here on the right-hand side, notice that I have kx minus kx, which drops out, and then omega t minus a negative omega t, which is 2 omega t. And then the 2's cancel out, and you end up with this. So here's basically what this expression says, and you'll see this mathematically in my example in a little while. But as time goes on, this number here cycles in between plus and minus 1. And then this term right here is not a propagating wave like, for example, say this term here or this term here from earlier, but instead it's just a sine curve. And then as this here cycles between plus and minus 1, this sine curve then causes a wave to oscillate in place, like so. That's why we refer to this as a standing wave. Okay, you'll see specifically how the trig works in a specific example in just a few minutes. But before we get to that example, how do we end up with the little pattern equations that you saw earlier in the previous part 1 of this lecture? Here's how we get these little pattern expressions. Okay, let me erase all this junk. All right, so now the patterns. Okay, let me just illustrate by drawing the n equals 1 standing wave. So once again, here's x, here's y, and then we have our length of string L like so. And then right here, for example, is the n equals 1 standing wave. Half a period later, oscillates to here. Here's 0, the origin. Here's the length L. Once again, the spring itself has length L. Okay, here's my expression. So, and now what we're going to do is we're going to apply boundary conditions to that expression. Okay, here's what I mean by that. Regardless of the time t, first of all, at the position x is equal to 0, notice that y is always going to be equal to 0. Now, yes, technically I'm sitting here and I'm moving my hand back and forth like so to maintain the standing wave, but the reason why I have to do that is because of damping. The energy would be lost as heat. If we ignore damping, once there is a standing wave, this portion of the spring is basically nailed in place. So in other words, at x is equal to 0, the function y is equal to 0. So now let me go ahead and set this equal to 0 here. And on the right-hand side of the expression, we have this, 2a sine of 0, and then sine omega t. Okay, divide the 2a out, divide the sine omega t out. In other words, those two terms don't matter. Like so. And then all that we have here is 0 is equal to the sine of 0. Quite frankly, this really doesn't tell us anything. However, it's the other portion of the spring, this boundary here, when x is equal to L, that's what's more important. So now let's take a look at that. Once again, this is known as a boundary condition. So notice that when x is equal to L, think of this as another person, for example, holding onto the spring. That person is just holding the spring in place. So regardless of the time t, the value of x, or rather when x is equal to L, the value of y is always equal to 0. So now what I do is I once again set this here equal to 0, and then the 2a and the sine omega t once again don't matter. They just divide out. But now take a look at this guy right here. Sine of k times L is equal to 0. So then therefore, what does KL have to equal in order for the sine of it to be 0? Well, one of the things that it can equal is 0. Well, we already know that because when x is equal to 0, y is equal to 0. Once again, that doesn't really tell us anything. However, KL could be pi. The sine of pi is equal to 0. Or it could be 2 pi. The sine of 2 pi is equal to 0. And so on and so on and so on. So then therefore, in order for this to occur, KL must be equal to a multiple of pi. Okay, and now remember what the wave number k is from my wave kinematics lecture. The wave number k is 2 pi divided by the wavelength. So, and now I'm just going to go ahead and solve for L. The pi's here cancel out like so. Cross multiply the other terms to the other side, and there it is. There's my pattern equation. In space L, you must have a multiple of half wavelengths in order for a standing wave to occur. And then because the frequency, once again, is the speed divided by the wavelength, if you solve for the wavelength here as 2L over n and then plug it into here, you then end up with the harmonic frequencies expression, like so. So these little pattern equations that you saw in the previous lecture, which are easy enough to pick up just by literally looking at the standing wave interference pattern itself, well, it's directly predicted here by the trig. Logging through the trig here, as you saw, is definitely a little bit tricky to do with the multiple use of these trig identities. Okay, exactly how does this kinematics equation here describe a standing wave? So at this point, go ahead and pause the film and then copy down the problem associated with standing waves from the lecture handout that I posted for you. Let me erase the board here while you do that. All right, so let me go ahead and copy down the problem. We're specifically given that the standing wave is for n is equal to 1, and here's our kinematics equation. And it's all in terms of meters, like so. Okay, so first of all, let's identify things. The amplitude of the standing wave itself, what you would actually see is 3 meters. The amplitude of the individual waves that I transmit down and the ones that reflect back would be half of that value. They would be 1.5 meters apiece. But you don't actually see those waves, of course, when you see the standing wave interference pattern. You just see the standing wave itself, and its amplitude is equal to 3 meters. Okay, and then we've got here, first of all, in part A of the problem, in trying to find the wavelength, we have the wave number k. So the wave number k is pi over 2 radians per meter. And then immediately from that, we calculate the wavelength lambda in the following way. Lambda is equal to 2 pi divided by k. So then therefore, this is equal to 4 meters. Okay, and then part B asks us to find the distance L between the endpoints. This is where the first of our 2 little pattern equations are going to come in. So L is equal to n lambda over 2, and then a little bit later on for the frequencies, the harmonic frequencies are nv over 2L like so. Once again, we're specifically given here in this problem that n is equal to 1, so then therefore the space L has to be equal to a half wavelength. This is equal to 2 meters. And then at this point, we start to graph out the wave. Okay, so in order to begin to graph out this wave as time goes on, as it first of all asks us in parts C and D of the problem, we have to find the period and the frequency. In order to do so, this is where the coefficient omega comes into play. So omega, the angular frequency, is given to us as pi over 4 radians per second. And then immediately from that, we can go ahead and find the period. So the period is 2 pi divided by omega. So 2 pi divided by pi over 4 is 8 seconds. And then therefore the frequency is the inverse of that. This is equal to 1/8 hertz. This 1/8 hertz, however, is specifically the quantity V over 2L. We're going to need that later on in the problem when we go to a different value of n. But for now, let me just note this here, that this quantity here is V over 2L. So this right here is part D of the problem. Okay, and then in part E, it says graph the function for quarter period increments of time for a full period. So this is similar to the wave kinematics that I did in last time's lesson. However, when you graph out a standing wave here for quarter period increments of time, it becomes very readily apparent very quickly as to how the pattern works. So now for part E, we first of all take a look and see what happens at times t is equal to 0. All that we do is we just go into the function and we set the time t equal to 0. When I do, I end up with a sine of 0, which is equal to 0. So y of x at 0 is equal to 0. So then therefore at this moment, what does this spring look like? Well, it's just completely flat. That looks like this. All right, so here's x, and here's y, and then here in black, for example, right here is the spring like so, and it's completely flat at this moment. Here's 0, and here's L. And then watch what happens for the next quarter period increment of time. So now I set the period here equal to, or the time rather, equal to 1/4 of the period. So this is 1/4 of 8 seconds. 1/4 of 8 seconds is 2 seconds. And now I go into my function and I set the time t equal to 2. When I set the time t equal to 2, I end up here with a sine of 2 pi over 4. That's the same thing as the sine of pi over 2, which is equal to 1. So if this quantity here is 1, then here's then the function that I end up with. Like so. So all that I have to graph out here is a positive sine curve with an amplitude of 3 meters. But when I draw it, I specifically have to draw it for one antinode, the n equals 1 standing wave. So then therefore that just looks like this. Once again, here's x, and by the way, all of this is in terms of meters. So let me be a little bit more rigorous about this as I go. And now I just simply draw the n equals 1 standing wave. And it's a positive sine curve, like so, with an amplitude of 3. So here is 0, and here is the space L. The space L, remember, is equal to 2 meters. Like so in the time between here and here, the spring has basically oscillated like so to its maximum amplitude position, where we have right here the antinode for the n equals 1 standing wave. So notice that I only drew there a half a wavelength. That's described by this expression here. The space L is 2 meters. The full wave, like so, would have a wavelength of 4 meters. Okay, watch this little pattern continue for the remaining graphs, and as I go through this process, hopefully you'll pick this up pretty quickly. All right, so let me move over to here. Now let's set the time, equal to 1/2 the period. So this is 1/2 of 8 seconds, which is 4 seconds. So now we go into the function, and we set the time t equal to 4. So when I set the time t equal to 4, I then end up here with the sine of pi, which is equal to 0. So then therefore the spring itself is completely flat again. So here's x in terms of meters, here's y in terms of meters, and then the spring itself, like so, is completely flat. Here in the space L of 2 meters. So in between this moment in time and this moment in time, the spring has oscillated back down to its equilibrium position. Okay, and then for the remaining 2 graphs, I'm kind of running out of room here, so let me go to here. So now we set the time equal to 3/4 of the period. So 3/4 of 8 seconds is 6 seconds. So then we go into the function, and we set the time t equal to 6. So when I set the time t equal to 6 here, I'm going to have then the sine of 6 pi over 4. That's the same thing as the sine of 3 pi over 2. The sine of 3 pi over 2 is -1. So I get a negative sign here multiplied by this. Like so. So now what I have to draw is a negative sine curve. But when I do, once again, in space L, we only fit into it a half a wavelength. So then therefore, it looks like this. So here's x in terms of meters, y in terms of meters, and now I just draw a half wavelength for a negative sine curve like so in the space L. So right here is the amplitude in the negative direction of -3. So you start off at t equals 0 with the spring flat, and then it oscillates up to its maximum displacement after a quarter period. It's flat again after a half a period, and then it's a negative sine curve at 3/4 of a period. Hopefully at this point you can guess that after a full period it ends up being flat again. And the last graph then therefore, that just looks like this. Now the time is equal to a full period here of 8 seconds. So then therefore we go into our function now, and we set the value of the time t equal to 8. When I set t equal to 8, then I end up here with the sine of 2 pi. The sine of 2 pi is equal to 0. So then therefore the function is equal to 0, and the spring is flat once again. Like so. 0 L equals 2 meters. So once you see how the pattern works here for quarter period increments of time, describing the kinematics here of this standing wave is actually rather easy to do. What happens, however, if we change the value of n? Okay, so the last portion of the problem, part F, reads as follows. Okay, repeat the problem for n equals 2. Assume that L remains the same. So the space between the two people, the space L, is not going to change, but now what one person does when creating the standing waves is they double the frequency. This then means that the black expression that I have up there on the top board is going to have to be adjusted. All right, so let me do some erasing here. Okay, now let's see. What do I want to keep? I want to keep this right here. The space L is 2 meters. I also want to keep this guy right here that I referenced earlier. Like so. Okay, and now specifically for part F, we switch to n equals 2. So when n is equal to 2, this then means that the value of the wavelength is going to be different than it was before. Now let's set the n here equal to 2, and then therefore in the space L, we have a full wavelength. So if L doesn't change, that's still 2 meters. Now the wavelength is equal to 2 meters. So when I draw this out in a few minutes, that means that I'm going to have a full wavelength that is drawn in the space L. This then changes the value of k, the wave number. It's no longer pi over 2 radians per meter. Here's how I find the new k. It's 2 pi divided by the wavelength. So 2 pi divided by 2, this is equal to pi radians per meter. So notice that the new value of k is nothing more than twice as much as the old value. In other words, it corresponds to the value of n. That's always the pattern, by the way, when you begin to adjust the arguments here of these signed terms. If this is the n equals 1 value of k, the n equals 2 value of k is twice as much, the n equals 3 is 3 times as much, and so on and so on and so on. Okay, and then we're also going to have to adjust the new value, or obtain a new value of omega, and the reason for that is because now the frequency is twice as much as it was before. So the new frequency here is 2 times the quantity V over 2L. From earlier, V over 2L, the fundamental frequency was 1/8 hertz. So this is 2 times an eighth. Therefore, this is equal to 1/4 hertz. So because we've changed the frequency now, this then changes the omega, and it also changes the period. So the period is the inverse of the frequency. It's no longer 8 seconds like it was before. Now in this case, it's 4 seconds. The new value of omega, that's 2 pi times the frequency. So 2 pi multiplied by 1/4, that's going to equal then pi over 2 radians per second. Like so. So notice that the new value of omega is twice as much as the old value. Once again, that's a simple pattern that gets picked up here as we adjust the kinematics equation. So if n is equal to 1, then you have this value of omega. When n is equal to 2, it's twice as much. When n is equal to 3, it's 3 times as much, and so on and so on. So then therefore, our kinematics equation here, specifically now for n equals 2, is as follows. Okay, same amplitude as before, that doesn't change. But now I have here, first of all, the new value of k, which is pi radians per meter, then multiplied by x, and then sine of the new value of omega, pi over 2, multiplied by time t. And then in terms of the graphs here, all I'm going to do is draw out the first 2 graphs for t is equal to 0, and then for 1/4 of the period. After that, you'll get the idea. All right, so let's see what first of all happens if t is equal to 0. So I just go into the function and plug in t is equal to 0, and when I do, I end up with a sine of 0, which is 0. So then therefore, like before, the spring begins as being completely flat. It always will be completely flat, by the way, at times t is equal to 0, unless we had an additional phase shift term here in the argument of the sine function. Don't worry, we're not going to bother doing that, however. All right, so at any rate, though, I'm drawing it. So x in terms of meters, y in terms of meters, and then the spring starts off once again as being completely flat. So here's the origin, here's the other person over here, a distance of 2 meters away. Okay, now watch what happens for the next increment of time. So 1/4 of the period. This is not 1/4 of 8 seconds, however. This is now 1/4 of 4 seconds, the new period. That's 1 second. So now we go into the function, and we set the time t equal to 1. When I set the time t equal to 1, then I end up with a sine of pi over 2 here, which is 1, and then therefore I just end up with a positive sine function. Like so. Well, when I draw this positive sine function now I have to fit a full wavelength in the space L. That then therefore looks like this. So once again, x in terms of meters, y in terms of meters, and now I just draw a positive sine function like so. Here's the space L, once again, of 2 meters, and I'm drawing it with 2 antinode. So I have a full wavelength here in this space L. After that, then the pattern continues in this manner in the following way. At a half a period, basically the spring will end up being flat again. At 3/4 of a period, it'll be a negative sine function. And then after a full period, it'll end up being flat again, like so. So at this point, you can go ahead now and do the assignment that I've posted for you in the folder called Handout Standing Wave Functions. Make sure you follow the directions for submitting that assignment. I wish you all very well. Today's shirt was corrosion of conformity. See ya.